And you've got at cathode, you're going to have Fe3 plus ions, you're going to have Cl minus 1 ions, you're going to have water at cathode, and you're going to have water at anode. Remember, no H plus 1, no OH minus 1 ions. So who's going to gain electrons? Is it Fe3 plus or H2O? So what you're going to do is just open the data booklet and you're going to look for equations in the forward direction. So you open the booklet and yeah, I just went somewhere over here. So you're going to look for Fe3 plus, and you're going to see those equations where Fe3 plus is gaining electrons. So Fe3 plus can gain electrons, right? So it's either this one or it's this one. So it's either minus 0.04 volts or 0.77 volts. And the other one, apart from Fe3 plus, was water. So there's water that could gain electrons as well. So who gains electrons? The one that has the highest potential. So it's going to be this equation in the forward direction. Is this clear?
Yeah.
And for the other reaction, you want to figure out who loses electrons, Cl minus 1 or H2O. So now look for the equations in the backward direction. Cl minus 1 should appear on the right side. So here's one, Cl minus 1 losing electrons, that's 1.36 volts. And there are two water equations where water are losing electrons. It's either this one or this one. So who ends up losing electrons? It's going to be, who loses electrons? The one that has the lowest potential. So it's going to be 1.23 volts, and that's going to be your equation. So is this clear?
Yes, sir.
Yes.
I said now we're going to quickly do Faraday constant, and Faraday constant is it simply means it's a constant. It simply means it's the charge on 1 mole of electrons. That's it. So it's in simple words, Faraday constant. It has a value of 96,500 coulombs. 96,500 coulombs. You have to remember that value. It's given in the data booklet, but it's better to remember that value. And it's in simple words, it's simply the charge that is present on 1 mole of electrons. That's it. So how do you figure out the charge on 1 mole of electrons? Because you know that on 1 electron, the charge is what? 1.6 times 10 to the power minus 19 coulombs. That's the charge of a single electron. If you've got 1 mole of electrons, how many electrons do you have? You've got 6.02 times 10 to the power 23 electrons. So if you want to figure out the charge on 1 mole of electrons, you multiply the two things and you're going to get something that's going to be close to 96,500 coulombs. Is this clear?
Yes, sir.
And the simple formula for that is that you have, it's usually written as F is equal to LE, where L is the Avogadro's constant. Number, and E is the charge on 1 mole of electrons. It's 1.6 times 10 to the power minus 19 coulombs. So in simple words, this is what the Faraday constant is. And you should simply remember the value of what Faraday constant stands for. And the purpose of the Faraday constant is that it gives you a conversion, a ratio that you can convert. You can convert the moles of electrons, and this is the ratio. I mean, let me write it explicitly. It's 1 mole of electrons. It's going to have a charge of 96,500 coulombs. Now, if you have this specific ratio, you can use this ratio to figure out if you've got charge. You can figure out the moles of electrons. If you know the moles of electrons that are traveling through the circuit, you can figure out the charge that's traveling. So you can convert charge to electrons or moles of electrons, or you can convert moles of electrons to charge. Another formula that usually goes with this is Q is equal to IT, which you already did in physics. It's a way of measuring how much charge is flowing through a circuit. I is in amperes. and T over here is going to be in seconds. So that's it. Most of the questions are going to be very straightforward. So for example, we're going to try and do a question like uh, at 1 ampere current is used to electrolyze copper sulfate for 45 minutes. Calculate the mass of copper deposited. So you're supposed to calculate the mass of Cu deposited. Now this is a very common electrolysis. You already know that the cathode equation would be this one: copper 2 plus gaining 2 electrons to form copper. And we are being asked to figure out the mass of copper that's going to be deposited. Now, two ways of finding out the mass. The first thing is you know the current and you know the time. So if you know the current and the time, you can figure out the charge, which is going to be Q is equal to current into time, which would be 1 ampere, which would be multiplied by 45 minutes, and every minute is 60 seconds. Can you even solve this and tell me what the answer is?
Two 2,700.
Kitna 2-1?
2,700.
2,700, right?
Yes.
So you're getting 2,700 coulombs for this. So we found the charge that's flowing through the circuit. Now I can convert that charge to electrons because I know that 1 mole of electrons, it has a charge of 96,500 coulombs. So I can use ratios and I can figure out that if I have 2,700 coulombs, how many moles of electrons are actually passing through the circuit? What would that give me? 2,700 divided by 96, 500. I think it gives me 0.0280. So it's giving me point. Can you even double check and tell me, is this the right answer?
Yes, sir.
So rounded to three significant figures, it's 0.0280 moles of electrons. So I figured out the moles of electrons. How many moles? It's 0.0280 moles. Is this clear? Now, based on this, can I figure out the moles of copper that are going to be deposited? Because I know the ratio that 2 electrons they deposit, 1 copper. So if I have 0.0280 moles of electrons, the amount of copper deposited is going to be half of that. So that would give me
0.14.
0.014, right?
Yeah, yeah, sir.
So you're going to get 0.014 moles. And once you have the moles of copper, you can find the mass, 0.014 multiplied by whatever the mass of copper is in the booklet. We can find that out. Usually it's 63.5. So where's copper? It is 63.5. So we're going to use. And what mass do we get? What do we get?
0.882.
So you're getting 0.882. And that's our answer. So the point is that the current that's flowing can be converted into charge, and the charge can be converted into the moles of electrons. And you can then use the moles of electrons to figure out the moles of all the substances. that are getting deposited during electrolysis. So is this clear to everyone? Shafaq, Lubana, is this clear?
Yes, sir.
So now most of the questions are going to be very similar. And most of the time, most of the questions are going to be very similar to this one. So it could be done in the reverse as well. Like they might give you the mass, so you can find the moles, and from that you can find the moles of electrons. If you find the moles of electrons, you can figure out the charge that's passing through the circuit. And if you figure out the charge that's passing through the circuit, and if they've given you current and they're asking for the time, you can calculate that. So most questions would be as straightforward as this. They would just give you, they would just ask you about time or the current that's passing through the circuit or the mass of substance that's being deposited. So is this clear?
Yes,
Yes, sir.
So now there's one other thing that you have to do, and that's we're going to move towards past papers now. Now there's one other thing which has been added in 2022, and that's minus n f e naught cell. So the thing is that Gibbs free energy, we did this earlier. I just have to do a bit of research on this. Like it's just a small thing that's been added. Obviously, there are no past paper questions on this, so I need to sort of read up on this because, like, what type of Cambridge questions do they expect? But most likely, the questions are going to be very, very simple. So, Gibbs free energy. Previously, when we studied entropy, we learned about Gibbs free energy. That's the total energy available to a system. If it comes out to be negative, then that basically means that the reaction is spontaneous. And if that comes out to be positive, then that means the reaction is non-spontaneous. That means that overall the reaction needs energy from outside. So there are two types of Gibbs free energy, and E naught cell, we've already calculated it. So we constructed all these cells. F is the Faraday constant, which we just studied. That's 96,500 coulombs. And N is the number of electrons that are involved in the reaction. The number of electrons that are being gained and lost, that's what N stands for. So N is that. You put them together, and if the value comes out to be negative, then that simply means the reaction is spontaneous. And if, or the cell that you have constructed is spontaneous, and if it comes out to be positive, that means the reaction is non-spontaneous. But we're going to leave this for another time because there are no past paper questions on this yet. So I'll just make a small worksheet on this, and we'll do this separately. It's just one formula. You just put this formula. If you haven't studied Gibbs free energy, we're going to cover that again as well. So we're just going to move towards past papers at the moment. Take it, remember this, just highlight this. Let me create a worksheet on this, a small worksheet, and then we'll do more questions on this. This is the thing that's been added to the 2022 exam, just one very, very small formula. Anyway, so moving towards past papers. And we're going to do electrochemistry past papers now. We've done all of it, all the theoretical parts. So this was electrochemistry, this one. So let's start with the first question, which is this one. And the first question, one second. This one is kind of a tough question. This one was probably the trickiest questions in electrochemistry. So you have this question. I'll first explain what's going on by using the data booklet, or I'll just simply explain it over here. What we have done so far every time is that we had two electrode reactions, right? So we had Na plus one electron. So I'm just explaining this so you can understand the first question. The E naught was minus 2.71 volts. And I've got a second reaction. And the E naught for that was 1.36 volts, right? And I'm just going to multiply the first one by 2 so that the electrons gained and lost are equal. So which of them would gain electrons? Which one would be the one that would be losing electrons? Out of the two, who gains electron?
Chlorine
Sodium
has
loses.
Okay, so it has a higher potential, right? It's going to gain electrons. And the other one is lower potential, it's going to lose electrons, right? And one second. I said the other one would lose electrons. So these two reactions. Now the thing is, how did we construct the overall equation? We just added the two equations up. What we simply did was we added up the reactants, we added up the products. Like the first reaction was going in the backward direction, so it's 2Na changing into 2Na plus 1 plus 2 electrons, and the second one is going in the forward direction, so I'm going to write it in the forward direction, and it was forming 2Cl minus 1. So what we did was we just added them up. Like in all our cases, we didn't actually write it again. We just added up the reactants. The first one is the reactant is this one, and in the second one, the reactant is this one. So I've just adding up the left side. I've sort of set the reaction straight. Like this is happening in the backward direction, so I've put it in the right way. So Na and Cl2 are reacting. Those are my reactants, and 2Na plus 1 and 2Cl minus 1 are my products. So is this clear so far?
yes, sir.
Yeah.
So this is what we have been doing, right? And E naught cell is high potential reduction potential minus oxidation potential, so it's 1.36 minus 2.71 volts. Now this first question, what they've basically done is they've actually removed one of the equations. Like you don't know what this equation is, so that equation is missing. They've given you the final equation, the overall equation. They've given you the first equation for oxidation. I mean, they've given you one of the half reactions. So that's your oxidation half reaction. And you have no idea what your reduction half equation is. So there's an equation that's missing in between. Like the initial equation is missing. They've given you the final equation. So is the question clear? The first one, like what's happening in the first? I mean, is this idea clear?
Yes, sir.
Now, how do you figure out this equation? Like if it's not given, but you're given this, you're just going to figure out the missing things, right? Like Cl2. So there has to be Cl2 over here because in the final equation there is Cl2 present. There's Cl minus 1. So you have to put in Cl minus 1 over there as well, right? 2Cl minus 1. And it's losing 2 electrons. So the other one should be gaining 2 electrons. So there should be plus 2 electrons over here. So is this clear? Shafak, Abdullah, is this clear?
Yeah, it is clear.
Yeah.
I said now,
Sir, I had a question.
yes.
E naught cell is equals to 1.36 minus this value. Why are we subtracting?
It's a potential difference between the two. Whenever you have an electrochemical cell, it's the potential difference between the. I mean, there's one electrode which has this potential. There's another electrode which has this potential. So what's the potential difference between, like, if you have a resistor and there's 10 volts over here and there's minus 100 volts over here. So what's the potential difference across the resistor? that's going to be higher potential minus lower potential. So it's going to be 10 volts minus 100 volts. So the voltage that would be appearing on the resistor is going to be 110 volts. Is this clear? Aruba, is this clear?
Yes, yes. Thank
I said, now just remember this. Okay, remember what we did over here is side पे. We're going to apply the same thing on this equation now. What they've done is they've told us that the overall reaction, they've given us the overall reaction, right? And they've given us the equation. So this is my overall equation. And this is my oxidation equation. So they've given us one of the half reactions. He's saying water is oxidized in this process according to the following half equation. So for this reaction, which is the overall reaction, they gave me this half equation. And they're asking, use these equations to deduce the half equation for the reduction of carbon dioxide in this process. So we're looking for the reduction equation. How do we figure out the other half equation? And he's already talked about the reduction of carbon dioxide. So I know that this other equation, it's carbon dioxide that's getting reduced. And I have no idea what's happening. TK, so I have no idea. But I know that this equation and this equation, they all add up to give you this. Right? I mean, this is what happens, right? It's this is what we did over here as well. How did we get the overall equation? We added this equation with the reduction equation, we got this. So is this clear?
Yes.
So now, so this would add up with this and it would give you this. Now, the first thing that you'll notice is that there's 6 O2s over here. Now, if you've got 6 O2s over here, I mean, these things are getting added up to give you O2s, right? So there has to be 6 O2 over here. I'm going to multiply this by 6. That would give me 12 water molecules, 6 O2 molecules. This one would become 24H plus 1. And this one would become 24 electrons. So why did I do that? Because I had 6 O2s in the product. So that means my half equation number 1, has 6 O2s in the product. So I need to multiply this equation by 6. So is this clear?
Yeah, but I think now you will cancel the O2s or
No, the two equations must add up to form this equation, right? Now, on this side, I've got 6 CO2s. So where are the 6 CO2s? I mean, these two are adding up, right? They add up to give you this. So on this side, I've got, I mean, this is the overall equation. So on this side, I've got 6 CO2s. So there should be 6 CO2s over here. I mean, that's the only way. So I figured out that the reduction equation must have 6 CO2s. So on the right side, I've got a glucose molecule. In the oxidation equation, there is no glucose molecule. So the glucose molecule probably came from the reduction equation. So it's going to be C6H12 and O6 over here. Is this clear so far? Shafaq Lubera, is this clear?
Yes.
Okay.
Yes, sir.
Now, so you've got a glucose molecule over here. So I have my 6 O2s now that they are coming from my oxidation equation. The 6 O2s over here. I've got my glucose that's coming from a reduction equation. I've got so what do I do with 24H plus 1 and 24 electrons? Now remember this, what we did over here was that the number of electrons, and let me remove this. So what we did over here was that I multiplied the first equation by 2. I made the number of electrons gained and lost equal. So if there are 2 electrons being produced on this side, there must be 2 electrons being gained on the other side. So coming back to this, if there are 24 electrons being produced on this side, there must be 24 electrons that must be gained over here. Right? Is this clear? Electrons gained and lost must be equal. Is this clear to everyone?
yes.
Yes, sir.
Another thing is, in the first equation, on the right side, there is H plus 1, 24H plus 1 being produced. Now, there is no 24H plus 1 on this side. That means the 24H plus 1 that were produced in the first reaction, they got consumed in the second reaction. So is that also clear?
Yes.
So the missing,
How did it got consumed again?
because they're not, I mean, when you added them up, you got the overall equation, right? So that means there is no H plus 1 over here. Abdullah, is this clear? There is no H plus 1. So that means if 24 H plus 1 are getting produced in the first one, 24 H plus 1 are getting consumed in the second one. Just like the electrons. Like, why don't you show electrons over here? Because the electrons all got used up. In the first equation, 24 electrons got produced. In the second one, the 24 electrons got consumed. Abdullah, is this clear?
Yeah, that was
I said, now the final thing is you've got to balance the water molecules, because the thing is, add up the left side. I mean, this is my, this is my left side, right? The left side must add up to this, and the right side must add up to this. The right side, I think, is adding up to this. Like the glucose and 6 O2 molecules, they are there. The 24 H plus 1 and 24 electrons are getting cancelled out, so that's gone. So this side is fine, the right side is fine now. The problem is with the left side now. Like if you add up the left side, you've got 12 H2Os and you've got 6 CO2s. But over here you have, I mean, they should add up to give you how many water molecules? They should add up to give you 6 water molecules. But you have 12 water molecules over here. That means 6 of the water molecules are probably getting cancelled out. I mean, that's the only way. Like you've got 12 water molecules over here and you add up this, it should give you this. And the only way that's possible is to get to 12 water molecules over here, you can subtract 6 water molecules. So there must be minus 6 H2Os over here. And now if you add up the left-hand side, it should give you this. Is this clear?
okay.
So what you're getting is, like, if I write this equation properly, what you're getting is this equation. Let me write this properly. This is the left-hand side, 6 CO2. And I've got 24 electrons. They're gaining 24 electrons, and they're 24 H plus 1 ions as well. And there's minus 6 H2Os as well on the left side. On the right side, I just have a glucose molecule. The H2O molecules can be taken on the right side, and it would become plus 6 H2O molecules. So that's my reduction equation. This is the reduction equation I'm getting. So I'm just going to repeat everything. I had a missing equation over here, which I did not know what it was. But they just told me that carbon dioxide was getting reduced. So I just had carbon dioxide to start with. And I knew it was getting reduced, so it was gaining electrons. I have no idea how many electrons was it gaining. Because my overall equation had 6 O2s, what I did was I multiplied the oxidation equation that they had given me, and I multiplied it by 6, so that when I add this equation with this equation, I get 6 O2s in my products. So I multiplied everything by 6. That gave me 24 H plus 1 and 24 electrons. Because there was no 24 H plus 1 showing up in my reactants or products, or 24 electrons showing up in my reactants or products, I therefore assumed that the 24 H plus 1 and 24 electrons being produced over here were being consumed in the second reaction. And I multiplied it by 6 because I had 6 CO2. So these two would add up to give you 6 CO2. So there should be 6 CO2s. Is this clear so far? Right?
Yeah.
And there was a glucose molecule over here, and this equation did not have a glucose molecule. So that means the glucose molecule came from this equation. So I put a glucose molecule over there as well. The only thing at the end was that when I add up the two blue equations, the half equations, they must add up to 6 water molecules. But on the left side, I have 12 water molecules. That means I need to get rid of 6 water molecules. In my second equation that I created, I added minus 6 H2Os. So that when you add them up, you get 6 water molecules. And when I rewrote this equation, minus 6 H2Os can be taken to the other side. It would become plus 6 H2Os, and that's going to be my reduction equation. So is this all clear?
Yes, sir.
ठीक है, Lubena, is this clear?
Yes, sir.
Achha, so this one was kind of tricky because you had to do a lot of working and think a lot on this one. As the next one is, you've got a fully labeled diagram that should be used to measure the standard electrode potential of oxygen in half equation 1 under standard condition, including all equations, all necessary chemical equations. So it's a fully labeled apparatus for measuring the standard electrode potential. For this equation, I'm going to write the equation. It's going to be, I think it was the original equation was 2 water molecules, reversible not six O2 molecules. There was only one O2 molecule. So you got O2 molecule plus I think 4H plus 1 plus I think 4 electrons, right? This was the reaction. And he's saying, what apparatus would you use? Now you have to construct an electrode. Now the electrode is, because it involves a gas, you need a gas jar. So you're going to take a gas jar, and the gas jar would have O2 gas being pumped in because he's using the term standard. So you have to mention the standard conditions as well. It's going to be at 1 atmosphere pressure. Now in the gas jar, you're going to put a platinum electrode. And what would oxygen gas react with? The oxygen gas would be reacting with H plus 1 ions. You need H plus ions, and you need water, which is obviously there. So it's basically H plus 1. And the concentration of H plus 1 is going to be 1 mole per decimeter cube. And we can write aqueous. That automatically means that there is water present. So is this clear how I've constructed the electrode?
Yes, sir.
And,
Yeah.
and also remember, there were 3 types of electrodes. One involving metals, one involving only ions, and the one involving gas. That's going to look like this. So now, how do I measure the standard electrode potential? What do I connect it with? Like I need to measure I have to label this as well. This is the platinum electrode. So all electrode potentials are measured against what? Like what's the reference electrode?
Hydrogen electrode.
Okay, so you have a hydrogen electrode and you're going to measure it against the hydrogen electrode, which is again a gas electrode. So there's going to be H2 gas that's going to be pumped in at 1 atmosphere pressure. And the solution is going to have H plus 1 aqueous. And the concentration is going to be 1 mole per decimeter cube. And there's going to be one more thing, and that is one thing is missing. What is that thing? Because
A salt bridge.
okay, so you have to mention a salt bridge. That is going to be added. So a salt bridge is missing. So you have to label and label everything. This is the platinum electrode. That one is a salt bridge. This is a voltmeter. Tiki, you can write voltmeter over here. So everything has to be mentioned. So remember, it's a 4-mark question. You're going to get questions on drawing of electrodes. Now, from the cell, use the data booklet to calculate the E0 cell and deduce which electrode is the. Now you're saying that this one is the hydrogen electrode, right? The hydrogen electrode always has a potential of 0 volts. That's your reference point. Now, water, oxygen, and H plus 1, you need to find this electrode. This is this one. So we can go and open the data booklet where we're going to try and find this one. It's probably this one, the one that I'm pointing to. It's oxygen and H plus 1, 4 electrons, water. That's the equilibrium reaction. And the value is 1.23 volts. So this one over here is 1.23 volts. Is that clear?
Yeah.
So for the cell drawn, use the data booklet to calculate the E0 cell and deduce which electrode is the positive one. So the positive one is the one that's at a higher potential. That's the positive one. So the left-hand electrode is the positive one, and you can measure the E0 cell, its higher potential minus lower potential, or reduction potential minus oxidation potential, and that obviously gives you 0 volts. So not 0 volts, it gives you 1.23 volts. So it's 1.23 minus 0. चलिए ठीक है. So is this question clear?
Yes, sir.
Yes.
चलिए ठीक है. Let's continue. Just remember, this one was a kind of a tricky question because I mean, this one was kind of tricky, but it was not that difficult. Yes.
Sir, is there any other way that we can do the question number 3, the A part, the first part?
No, that's probably, there might be, but that's probably the only way. Like, it's you're just looking for the missing equation. So just one second. So that's the only way probably. Now the real problem in this one was that most equations are kind of straightforward, like the ones that we did over here. I mean, this was very straightforward. If this was missing, you can kind of easily calculate this, right?
Yeah.
The only reason that was kind of slightly more difficult was that it involved substances that were appearing in the reduction equation that were actually not appearing in the final equation. I mean, for example, the 24H plus 1, they're missing over there. So that means they got consumed over here. So there were things that were appearing over here that when you add the two equations up, they get cancelled out and they don't show up over here. Okay, so that's why this one was kind of slightly more difficult.
Got it. Okay.
Okay, let's continue tomorrow with the same past papers, right? Okay.
Sir, can you send this worksheet to us on the group so we can practice it?
Okay, I'm sending it.
Okay. Yeah.
Okay.
And even the whiteboard link.
Yeah, sure.
Okay.
Okay then.
Thank you, sir.
Allah Hafiz. ये ऑन करते हो ऊपर